Assalamualaikum and good day everyone. Okay, today we're going to cover week 5 of the lecture, which is about the electrostatic field in a medium. Okay, before this we study about electrostatic field in week 2. Week 3 we study about flux density and divergence theorem. Week 4 we study about potential difference and energy density. Okay, all of these consider free space condition. Okay, so now in this lecture we're going to consider two kinds of cases, okay, which is the conductor and the dielectric. Okay, so that will be our medium. Okay, we study here in this week of lecture is the conductor and the dielectric. Okay, this is both extreme case. Okay, so conductor and dielectric. In between them we have semiconductor. Okay, but we're not going to cover in this EMT subject. Okay, we only cover both cases, conductor and dielectric. So you guys can refer to the study group. Okay, for the week 5, okay, the electric field in material space. Okay, you guys can read for more detail. Okay, so without further ado, I would like to start. Okay, I will be based on the presentation slide and I will do some demonstration afterwards. Okay, and of course you can watch the supplementary material. Okay, the lecture the lecture link that I share to you guys, so it will complement your understanding. Okay, on top of my lecture. Okay, so in conductor we will learn about current and resistance. Okay, just like a normal resistance that you know, which is in ohm. Yes, the same unit as in ohm. However, this we will use field theory. Okay, we use field theory in order for us to sample the resistance at particular surface. For example, if you have this, if you have this, right? Okay, you want to measure what the resistance. You can, as long as this is conductor, there is resistance. Okay, and the dielectric, you will study about boundary condition, capacitance, which you guys know about, and the energy. Okay, so capacitance is actually a conductor with dielectric in between. Okay, so your dielectric can be any material or it can also be free space. Okay, so what have you guys studied before in the previous lecture? Okay, you guys study about rho v. Okay, you guys also study about electric field density, electric field intensity, the potential, and the work done. Okay, and the work done. Okay, this consider that we studied before is in the free space. Okay, now in this lecture we will need to have the three important criteria that we need to know is that we need to know the material that we will use. Second is the applied field. Okay, why applied field is considered? Because we need to have the field, only then we can measure the resistance and so on, okay, and the current, okay. And the 4 and the 3 is that the moving charge particle, okay, charge particles. So in our system, what is actually that is moved? I think you guys also learn in your secondary or your foundation is the electron, right? Okay. Now there is 3 parameters, okay, that we use in order to classify whether that material able to permit the field that pass through it, okay. So we have 3 parameters, which is this, which we call permittivity, okay. So it can be, for example, like this for free space, and this one is with respect to the material, okay. Then the next you have permeability, okay, and the next you have conductivity, okay. This we measure in cement, okay. So next, imagine we have a current, okay. Imagine we have a current. Okay, imagine we have a current, okay. So in this chapter, okay, you guys will study about 3 models of current, okay. Means we will have 3 different kind of equation for you to obtain the current, okay. Now before we further ado, we proceed, okay. So let's say you have a section of a wire, okay, that under electric field, okay, you need to behave electric field, okay. Then we will have here the current density, okay. We call this as current density, okay. Don't mix up with the current I, okay, it's different, okay. We also notice that J is actually proportionate to the electric field intensity, okay. So far so good, okay. Because this is proportionate, if we put like this, okay, and we want to put into equation, then we have some constant, okay. So the constant here is our conductivity, okay. So the units for this is A per meter square, okay. Okay, now we try to know about this, okay, about this guy now, okay. So conductivity is the products, okay, is the product of the charge density and the electron mobility, okay. You guys can see the supplementary material lecture video for how he explained maybe in more detail compared to me, okay. It's okay as long as you guys understand. I won't mind, okay. It's for your own good. So okay, good. So when you have a conductor, For example, okay, when you have your electric field, then you have a moving charge particle. Okay, what is it? It is a electron. Okay, and you guys know, right? The electron moving opposites. Okay, opposite direction. So it's here. Okay. So the product. So conductivity is the product of the charge density of the electron. This in opposite directions, and also this is with respect to the electron. Okay, so here this one is your charge density, and this one is your electron mobility. Okay, how mobile it is. Okay, okay. We also know that when in high temperature, okay, if we increase the temperature T, the conductivity will be also increased. Okay, conductivity is measured in unit Siemens per meter. Okay, now, okay, we see the examples of the material, okay, that we have. Okay, for example, we consider a material, for example, we have medium here. Okay, for example, we have, imagine, for gold, silver, okay, and also, for example, dry earth. Okay, this one you can get from your slide. Okay, so the conductivity here, okay, for the gold, you can see it is 4.1 times 10 to the power of 7. For the silver is 6.1 times 10 to the power of 7. And for the dry earth is 10 to the power of 5. Okay, you see, this one is in the unit of Siemens per meter. Okay, so if you can see, the one with higher conductivity will be conducting electric more efficiently, of course. So this one is considered conductor. Okay, and this one, you see the conductivity is very poor, so this one is actually insulator. Okay, so here you can see that you can see that sorry, this one is in reverse. Okay, so conductivity is increased. Okay, with so the next, you will study about if you have like a region here. Okay, then you have here, this is your applied, okay, electric field. Then you will have a positive charge at first at the other section, and you will have a negative at here. Okay, so it will arrange itself. Here is the positive and here is the negative. Here the electric field here is 0. So the polarity of surface charges depend on the direction of the external E field. Next, okay. So in the slide you can study, it will show about the rho v, okay, but we don't need to go to it further, but you guys can read if you want, okay. We will cover it later on, I think. Okay, okay, this one, okay, you guys can read it. This is at the slide number 9, okay. So the next, okay, this is the equation of the I, okay, just now what, okay, we have the J, okay. Now we trying to relate, okay, like what I told that there we have 3 model current, okay, 3 model current, okay. So the first model current, okay, the first one, you have I equals to dq over dt, okay. So this one is with respect to time, okay. So I is actually the electric charge passing through an area per unit time, okay. Thus, in a current of 1 ampere, for example, in current of 1 ampere, charge is being transferred at a rate of 1 coulomb, okay, 1 coulomb in 1 second, okay. Now we have learned about this J, okay, current density, okay. So if we have a current, okay, if we have a current, for example, okay, sigma this delta I, okay, flows through a plane surface, for example, just for example, okay, plane surface through a planar surface, the current density is, let's say this one is your planar surface, okay, del S, okay. So the current density passing through here is actually J equals to del I over del S, okay. So J is a vector, okay, so because it has direction, you see here, okay. Rearranging this guy, okay, then you will obtain, okay, rearranging slowly, okay, then we take normal to the surface, okay. When we take normal to the surface, this one should have some vector direction to it, okay. So then we have like this equals to J, okay, dot, okay. When we dot it later on, the thing that have the same direction will get some value, while the one that orthogonal will be 0, okay. So and then this one, okay. And if we consider a surface, okay, further if you want to see the total current flowing through a surface, okay, a continuous surface, what I taught in the previous lecture, if it's a continuous, it will be, we need using what, sigma or integral? It's integral. So the I, okay, a surface integral of J dot ds, okay. So you know what equation that you have studied, which is this. Okay, and you study about this. Okay, and you know about this. Okay, what else? This one later on. Okay, so the current density here, okay, you see, is ampere per meter square. You guys know what does it mean? It means that current density at given point is the current through a unit normal area, okay, at that point. Okay, unit normal area mean we speak about area is a surface. Okay, so I don't want to waste. Okay, now what else we need to study? Okay, so you guys can read from page Sadiku also. Okay, Sadiku page of Sadiku chapter 5 page 181 and so on. Okay, you can guys read to have a more detailed reading. Okay, now we want to, for example, we want to study the case of conductor. Okay, okay, we want to study about influence of electric field. Okay, if we applied electric field or we don't apply an electric field, for example, like in under static condition. Okay, okay, now okay, I think you guys can see here. Okay, okay, so here you guys see this one, we have two conditions. Okay, this one is isolated conductor. Okay, we just see this case first. Okay, let me close. Okay, we close this for a while. Okay, just wanted to see this. Okay, so if you see, this one is the E is the external electric field applied. Okay, so initially, okay, a conductor should have abundance of charge that is free to move. Okay, a conductor. So we consider an isolated conductor, okay, such as shown in this figure. When we apply an external electric field, this one we applied, okay, is not exist naturally, we apply. Okay, then the positive free charge are pushed along the same direction as the electric field. Okay, as the same of applied field. The positive, okay, will be pushed towards here. But for the current, for the electron, for the negative free charge, is moving on in the opposite direction. So you have your you have your negative here. Okay. Then after some time, it will separate. Okay, it will separate. Then you have a region of positive here, and you have a region of negative charge here. Okay, so this is a surface charge. Okay, you will have a surface charge. So it's an induced surface charge because it is not naturally there before. Okay, so you have a surface charge already. Then here, because we have obtained this right condition, it will induce an E field, okay, which is this one. This one is the internal E field, okay. And what happened after that? This one will cancel out with this one, okay, cancel out with this one, okay. So cancel out. It will become the result in figure 5.2b, okay, when they have been cancelled out, okay, then you obtain this, okay. Now you obtain a conductor has a zero electric field under static conditions, okay. So here you have your rho v 0 and your E is 0 because it's cancelled out already, okay. Then you have the E here, okay. This one is your applied electric field, okay. So inside here it is 0, okay. Outside is still the same, okay, inside this region, okay. Okay, then we come to know that inside a conductor, okay, inside conductor, E is 0, okay, the vector electric field intensity is 0, okay. Therefore your rho v is 0 and VAB is equals to 0 inside here, okay. So VAB is the potential difference between point A and point B in the conductor. For example here, okay, point A and point B, okay, take a point. Okay, now you want to know another concept, okay. We want to go about the resistance now, okay. We want to go about resistance. So what have you guys learned in your secondary or the general terms that you know, the Ohm's law? Okay, Ohm's law. Ohm's law teaches us that V equals to IR, okay. Now you want to obtain the R, okay. So what have you learned? For the V that you have learned in the previous lecture, it is actually what? Line integral, okay. And you have E vector dot dl, okay. And what I that you have learned just now? J ds, right? And you also know that J is actually this, right? So you can further extend, sorry, okay. And this one, because this is constant, you can take it out. But you see the question, okay. Sometimes they make it a bit tricky that this constant have component inside, maybe R, whatever, okay. So you cannot put them directly out. You need to see the function, okay. So you learn, okay, this. Now you learn the concept of resistor now, okay. Then how you obtain, okay. Also, okay, the other way to get the R, okay, also the same is V over I, okay. This is one of them, okay. Other, you can consider, for example, okay, you just imagine we exploded, make it bigger, the structure, okay. so that easy to visualize. Okay. Now you see this is your positive and this is your negative, so this will be your applied electric field. Okay, correct? Then here along this you will have a length, and this one is your surface. Okay, then you know current, the conventional current move from positive to negative, right? So you have this as your current. Okay, direction. So because you have this as your current, conventional current, so you know electron current, okay, electron move in opposite direction, so here. Okay, so this move in opposite direction. Okay, here. Okay, now for the R with this surface, okay, we can use R equals to V over I, okay, for the case of normal Ohm's law. Then you have your L, the length of this conductor. Then you have your conductivity, and also what you have, you will have your S. Okay, S is the surface. Okay, the cross section. Cross section area. Okay, so now you have two equations of getting the R, right? You can have this, or you can have this or this. Okay, you can read further equation 5.18, 5.19, 5.20 for the P power. Okay, and more detail in this from the study book. Okay, now we want to do practice exercise 5.1. Okay, how we can use this equation that we have learned so far. Okay, you mentioned here for the current density J equals to 10Z sine square phi, okay, in the direction of the radius A over meter square, find the current through the cylindrical surface where radius is 2 and you have Z equals to 5. So again, I repeat, I don't want you guys to confuse. Okay, this is just radius. Okay, you can use R, you can use rho. Okay, but I will use R. Okay, so that we don't confuse with the charge density. Okay, now we try to wait, how can I do this? Because I want you guys to see the question and also the solution. I think this one is okay. So first, as that I teach you guys, just draw the axis. Okay, then normal cylinder you see is R2. Okay, so R2 here, radius. Then just draw your cylinder. Okay, I'm not an artist, so you guys just have to bear with me. Okay, so this is cylinder. Okay, that's not good cylinder anyway. Then it measured at Z, and it said is Z equals to 1 to 5. Okay, so here we can take, here is Z equals to 1. Okay, it's okay, you can take Z equals to 1 here. Okay, because doesn't necessarily start with Z0. Okay, so this can be your Z equals to 1. Okay, then this can be your Z equals to 5. Okay, now the question asks, okay, for the current density J, I rewrite again. Okay, so that you guys will be able to understand more better. Okay, so this is unit radius. Okay, unit vector in the r direction, so use r. Okay, so find the current through the cylindrical surface. Okay, now just we use this, okay, because it's about surface, so definitely you will use this equation. Okay, don't complicate. Okay, this is surface. Okay, it means double integral. Okay, now you have your j, but you have already your j, right? But you don't know your ds. Okay, so you see this is in r direction. Okay, then you just have to find the one that is the same r unit direction in in direction of r. Okay, because this is a dot product. Okay, anything that orthogonal is 0, so don't waste our time. So we know it is about this surface. Okay, and you see the j is flowing out. Okay, so this is your j. Okay, so what is the corresponding surface for this? Okay, it is r d phi, correct? R d phi and dz, and we must have the same direction in order for it to be non-zero, so it is r unit. Okay, we need the vector r. Okay, so this one is your ds. Okay, okay, so just okay, I don't want to, okay, just figure this. Then z is what is, then z sine square phi. Okay, and also r d phi dz. Okay, so you guys see d phi and dz here, so means it is the variable. Okay, we change the value. However, r doesn't have the r, so it's a kind of constant, so you put r outside. Okay, so that it won't complicate your calculation. Then 10 is also a number, just put it out. Okay, then you're left with z sine square phi d phi dz. Okay, then you have 10r. Okay, okay, this one is a bit complicated, right? Okay, this one I think you guys studied before, because prerequisite of this EMT is actually mathematics engineering. Correct me if I'm wrong. So this, so you guys need to be expert already. Okay, so not all will be given in the formula. Okay, during the exam. Okay, and also, okay, so this one, okay, you guys can actually settle from, you have cos 2x. Okay, this is the general equation. Okay, then you also know that actually cos 2x plus sine 2x is equal to 1. Okay, so you do some substitution. Okay, you will obtain sin square x equals to half minus cos 2x over 2. Okay, so I just use directly. Okay, put it inside. So you have z half minus cos 2 phi. Okay, because it's actually phi, right? Just phi, and 2 d phi dz. Okay, then 10r. How about z? It will be, okay, and what is the limit of z? It's between 1 and 5. Okay, and how about this one? It's actually phi over 2 minus cos, you will get sine 2 phi over 2, then integrate, differentiate inside, you get another 2. Okay, so what is the limit then for the phi? 0 until 2 pi, because it's full turn. Okay, your phi is here, moving from here. Okay, so it's full, so you need to know how to take the limits. Now we don't want to make calculation become difficult. You just take out 10 to divide by 2, you will have 5r. Okay, then you have 5 square minus 1 square. Okay, and for the sin, okay, for here, you know that 0 over 2 is 0, and sine 0 will be 0, right? So actually this one, okay, we don't, it's still 0, so we just take this answer. Okay, because sine 2 pi or sine 4 pi, sine 360 is all results in 0. Okay, so then, so we just take it here, so you have 2 pi over 2. Okay, then 5r, how about inside? 25 minus 1, you have 24. Okay, this one, just this, then you have pi. So how about your r? Okay, your r is constant. Okay, what is the value of r dimension here? R is 2, so it's 2. Okay, so 5 times 2, okay, times 24 times pi. Okay, what do you get? 5 times 2 times 24 times pi, so you get 754. Okay, so the question is asking about current, and you guys know it is ampere. Okay, so you guys can try the example here. Okay, okay, and we will cover, and then what have we learned so far? We already learned about the two models current. Okay, two models. So where is mine? Okay, I DQDT, I JDS. Okay, you learn about this SEO for resistance, and you learn about this. Okay, and okay, I think I need to maybe, okay, so today is 11 April. Okay, so this is page 1, because maybe you guys want to ask me, and I forget which paper are you guys are referring to. Okay, so I just put number, so give you reference later on. Okay, you guys can try out, okay, the exercise, and let me see. Okay, this is polarization. But I think polarization not yet. Okay, okay, it's okay. So you guys can, okay, you guys just see this first. Okay, and we will see in the next lecture. Okay, thank you.